Hi, everybody. Let's talk about stoichiometry. Stoichiometry is the science of measuring stuff, or more specifically, calculations involving stuff. And you might see this with mole to mole calculations, with mole to mass, or mass to mass calculations. And what that means is that you're going to have to convert from moles of one thing to moles of another thing, or of one thing to mass, or mass of one thing to mass of another thing. But where the nuts and bolts of it come in is with chemical reactions. And we use stoichiometry to calculate the quantities in a chemical reaction. So let's take a chemical reaction. So the reaction I'm going to use is one in which we have methane, CH4, reacts with oxygen to produce carbon dioxide and water. And we might want to calculate how much CO2 we get, how much oxygen we need, or how much water might be produced. We can calculate any of those things using stoichiometry. But before we can actually do the stoichiometry, we have to have a balanced equation. So let's balance this equation. I have 4 hydrogens over here, so I need 4 on the other side. So the way I'm going to do that is I'm going to put a coefficient in front. When we're balancing equations, we can only use coefficients in front. We cannot change the actual formulas of the substances involved in the reaction. So now I have 4 hydrogens on both sides. I already had just 1 carbon on both sides. But now I have 2 oxygens on this side, but I have 4 on this side. So to get that to balance, I need to put a 2 in front of this. So now I have 4 oxygens on both sides, and everything is balanced to this point. So now that we have a balanced equation, let's suppose that we want to calculate the amount of water that we might get. Well, before I do that, let's first look at how we can interpret this chemical equation. One way to interpret this is that we have 1 molecule of this, 2 molecules of this, 1 molecule of this, and 2 waters. But we don't typically, when we're doing stoichiometry, we don't typically interpret it that way because we can't see individual molecules. So we usually count by large chunks called moles. And that would mean we'd have 1 mole of this, 2 moles of this, 1 and 2. And so that's how we're going to interpret this equation. So that means that if I have 1 mole of CH4, I need 2 moles of oxygen to react, all of it, and I will get 1 mole of carbon dioxide and 2 moles of water. It is also a ratio of everything in the equation. For example, the ratio of CH4 to H2O is 1 to 2. So if I wanted to take, say, I wanted to react 4 moles of CH4, I might want to find out how many moles of water I would get. Well, since it's a ratio of 1 to 2, I'm going to get twice as many moles of water, or 8 moles of water. And that's one way to interpret it. But let's suppose that I don't have whole numbers. Let's say I've got 0.25 moles of CH4. Well, what the equation tells me is that I'm going to need 0.5 moles of O2, 0.25 moles of CO2, and 0.5 moles of water. But then again, we run into a problem because the mole-to-mole calculation doesn't really, we don't have anything in the lab that measures in moles. There's no instrument that can measure moles. So what we typically do is we start out with mass. So let's say we have 10 grams of CH4. And I want to know how many grams of water that would produce. Well, typically the way we do this is we use dimensional analysis. So our given is 10 grams of CH4. So that's what I'm going to start with. I'm going to start with my 10 grams of CH4. And I'm going to do some dimensional analysis. I'm going to use the train track method, as it's often called, where I don't put the multiplication symbols in here, but that's what we're doing, essentially. So in this case, I need to know the molar mass. We'll use molar masses a lot when doing stoichiometry. And molar mass is how much 1 mole of that substance would weigh. Well, if I look on my periodic table, I see the mass of carbon is 12, and the mass of hydrogen is 1, and I've got 4 of them. That means total, when I add all of that up, I get 16 grams of CH4 per mole of CH4. Okay, that allows me to cancel my grams of CH4, which ultimately I want to have grams of H2O. Now I can use my recipe, my chemical equation, which is basically a recipe for reacting CH4 with oxygen to produce carbon dioxide and water. That's our recipe for this reaction. And my recipe tells me that I have here a 1:2 ratio. So I'm going to put down 1 mole of CH4 will produce 2 moles of water. And now I can cancel my moles of CH4. And you often want to write down the substance you're talking about so you know which one you're canceling, because you can't cancel moles of CH4 with moles of H2O. No, you have to cancel moles CH4 and moles CH4. Now I have one step left, and that is to get it from moles to grams. Well, I'm going to use molar mass again. And again, hydrogen is 1, and I've got 2 of them. And then oxygen is 16. So that is a mass of 18. And I'm finding all of those on the periodic table. And I rounded everything to whole numbers just to make it, just to simplify the equation and the mathematics. So 1 mole of water will weigh 18 grams. That allows me to cancel my moles of water. Now I'm in grams of H2O. So what I have to do now is just some number crunching. So I'll get my calculator. So my calculator tells me it is 22.5 grams of water. So since I was only given 2 sig figs, or we'll assume this was 2 sig figs to be to be unambiguous, I probably should have written it as 1.0 times 10 to the first. But since I have two sig figs, I'm going to say 23 grams of water. And that is the amount of water I get when I react 10 grams of methane, CH4. And that is how we do stoichiometry. Later.